Hello friends, today we'll discuss about a data structure called union find disjoint sets. This is also known as DSU, Disjoint Sets Union. What this data structure provides is it provides a representation for collection of sets and two major operations in an efficient manner. What those two major operations are? First is find, given an element, find which set it belongs to. Let's name this operation as find set x. And given two disjoint sets, make a union of those sets. So let's say name it union set, and let's say a comma b. Okay, so what does, first let's make it clear what efficiently means. Efficiently means on an amortized base and constant time. I'll go over what exact time it will take. Let's say amortized constant. Now let's go over representation of this data structure. So for each disjoint set, we have a unique identifier or representative of that disjoint set. Okay, and each disjoint set is represented as tree. For example, let's suppose this is the first disjoint set, this is second, and this is the third. So 1, 2, 3 will be represented as, let's suppose, is a tree in tree form 1, 2, 3. We'll see how these edges are formed in next slide. And 1 is chosen as the representative, that is the root element will be chosen as the representative. Similarly for 4, 5, 4 is the root, hence the 4 is the representative. For 6 there is only one element and it's the root only, so this is the representative. So in a way, DSU is represented as collection of, or you can say forest of trees. Now let's go over the naive implementation of this data structure. Since we have to maintain the root of the tree, because that is the representative of each disjoint set, let's maintain a parent array. Okay, now let's see how both the operation will be implemented. First, go over the union set. Let's say we have to do union set over two elements a and b. We'll first find the representative of a, then representative of b. X and y are respectively the representative of a and b. And if x and y doesn't belong to same set, then just put the parent of y to be x. This is simple operation. Let's go through an example. Suppose this is the first disjoint set and this is the second disjoint set, and we have to make union of 2 and 5. So we'll first find the representative of 2, which is 1. Then we'll find a representative of 5, which is 4. We'll make the parent of 4 to 1. That is, now 1 will be the parent of 4. And you can see at the end figure will look like this. Now let's look at find set A operation. First we'll check the A itself is not root element. If it is a root element, then just return that element itself. Otherwise, do same operation of find set to the parent of A. Let's go over an example. Let's suppose you have to find representative of 7. So you will start with 7. You'll see that 7 is not the root element. It will go to 3, then to 2, and finally to 1. And 1 is the root element, and it will stop there. Okay. So in worst case, what can be the complexity? Big O of n. When worst case is possible when it's a skew tree, right skew or left skew. Okay, this is the case for both the operation. Even in the union set, the worst case will be on. Why? Because we do a find set operation and it can be on in the worst case, where n is the number of sets, or you can number of disjoint sets in the initially we have. Implementation, we saw that find set operation was on. let's see how can we improve it. So we'll do a path compression optimization. So what we previously was doing was we started from 7, we moved up and up till we find the root. Now we have to move up, but also what we will do is we'll break all these edges and we'll form edge between this to the root. That is, all the elements which comes in the path are now directly connected to the parent. This is called path compression optimization. So finally the tree will be looking like this. So what all nodes we processed while finding the set of 7? 7, 6, 3, 2. So all those nodes are now the direct child of the root. Okay. So this optimization makes big of log n on an average for each query, for each find set operation. We'll go over the proof in the next video. Let's go over one more optimization, union by rank / size optimization. This is done on union set operation. Let's first go over union by size. In union by size, we maintain additional info, that is size of each disjoint set. And while taking union, we'll merge tree of smaller size as child to tree of larger size. Let's go over an example. Let's suppose this is the first disjoint set and this is second, and we have to merge 1 and 6. First we'll find the representative of each set. 1 is the representative of itself and 6 is the representative of itself. Then we'll see the size of this is 5 and second is 3. Since this is the smaller one, the smaller tree will become the child of larger tree, and we will finally update the size of this larger tree. The final tree will look like this and the final size will be 8. In case both the sizes are equal, we can choose anyone as parent, another one as child, and we'll update the parent. Now let's look union by rank. Let's first define what is rank. Rank is the upper bound of the height of the tree. So we have seen that each disjoint set is represented as tree. So what will be the upper bound of the tree is called the rank of the tree. So in previous union by size we were maintaining size. Now we'll maintain rank of each set. And while taking union, we'll merge tree with lower rank as a child of the tree with greater rank. Let's see an example. Suppose this is the first disjoint set and this is the second one, and we have to merge 1 and 6. So clearly the rank of this is 3 and rank of this is 2. So we'll merge this as a child. So in case we have equal ranks, we can take anyone as parent and a second one as child, and at the end will increase the rank of parent. Equal rank, we have to rank of parent increase. We have to increase. This optimization, both the optimization union by rank as well as union by size, gives O log n of on an average complexity for each query. Now let's do a time complexity analysis of both the optimization. If you take both optimization, path compression and union by rank or size, we'll get amortized time constant, time per query as constant. What this function is, this is an Ackermann function on n, and it grows very slow. That is, if for 1 million n is equals to 1 million, it is less than 5. So it gives almost a constant amortized time per query. If we use only path compression, then O log n on an average, and if we use union by rank or size than O log n on an average. We'll go over the proof in the next video.